Okay, we're now going to start to study the so-called LC circuits. This is the first combination with two elements in the electronic circuit that does not include R. We have studied RL and RC circuits before. You know, whenever there's a resistor and whatever current that goes through a resistor, some heat will be generated. Okay, so a resistor takes other form electrical energy and turns it into heat. But here we don't have a resistor. We only have a capacitor and an inductor. So we call it an LC circuit. You know, a capacitor can store electrostatic energy, right? By storing charges on the plates or by creating an electric field. And what about the inductor? You know, once you drive a current through the inductor, once a current has been established on an inductor, the inductor will store magnetic energy. Okay? And then suppose I start with a certain amount of charge on these two plates. So the capacitor is initially charged and there is no current running. Okay? And then at that moment, of course, there is only one form of energy in the system, which is electric energy. Now suppose I close the switch so a current can start to flow. Okay? Then of course, as time goes by, the charge will diminish over time, but the current will start to establish. So now there will be some energy transfer between the electrical form and the magnetic form. But you see, there is no heat generated. Okay? There's only a transfer of energy between the two forms of electromagnetism, namely electrical energy and magnetic energy. The overall amount of energy, if you add both the electrical energy and the magnetic energy, that should remain a constant because there is no mechanism to take that electromagnetic energy and turn it to anything else due to lack of a resistor. So we can expect the energy to alternate between the electrical form and the magnetic form. Okay, yet keeping the total energy as a constant. Now, this reminds us of something we studied in Physics 1b, the so-called mechanical oscillation. The simplest example would be a spring mass system. Okay, here's an ideal spring attached to mass. There's no friction. Now you pull the mass to one side, let go of it, it starts to oscillate. Right? In this case, there are also two forms of energies. One is the kinetic energy of the mass, and the other is the elastic potential energy of the spring. The two forms of energy can alternate between one another. They can transfer between one form and another, and yet the total, the sum of the two, remains a constant. Okay. Now, is there further similarities between the LC circuit and the spring mass system? We wish to exploit the similarities between these two cases so that if we can establish a one-to-one correspondence between these two cases, then whatever we know about the spring mass system, we can sort of translate it into the language of electromagnetism in the LC circuit, so we can learn a lot about the LC circuit without starting all over with the mathematical calculation. Okay, so there are two functions that you study in the case of a spring mass system. One is the displacement function x, okay, and the other is the velocity v, which is dx over dt. Of course, you know one, you find the other. Here we have something very similar. We have a charge q, right? We also have the current I. Now I is dq over dt, just like v is dx over dt. Okay, and then so we suspect that there is a similarity, there is a correspondence between the charge on the plate and the displacement. If that's the case, then you can imagine that dq dt, which is the current, would correspond to dx dt, which is the velocity. Okay, now we can plot x as a function of time, right? We can plot as x as a function of time, and qualitatively we know what it looks like. Suppose I start. Okay, let's start by pulling the mass all the way to an extreme position, let go of it. So x starts with the largest possible value and gradually goes down, passing through the origin, and it goes to a negative value and then comes back again. So x goes as a function of time like that, right? It's a cosine function. We know that. What about q? Well, we said that at t equal to 0, the moment you close the switch, these two plates are fully charged and there's no current running at that point. So it corresponds to the case where the mass has been pulled to one side and let go from rest. So initially there is no velocity, just like there's no initial current, and then so Q starts from the maximum value, right? And gradually it has to go down because there is a current running, there's a discharging current running, so it's going to go down. Okay, now when Q becomes 0, right? When Q becomes 0, there is no electrical energy stored on the capacitor anymore at that moment, but the total energy remains the same, so the magnetic energy has to become a maximum, so that means the current is a maximum. Okay, in other words, dq dt has to be maximum, so you have the largest slope possible. It is not going to stop. Q is not going to go down to 0, remain 0. It's not going to remain 0 because there is a slope, so it's going to keep on changing. Okay, it's going to keep on changing. Q becomes negative now, which means this side is now positively charged and that side is now negatively charged. Okay, and then once you reach a certain point where Q becomes a maximum value, okay, with a maximum amount of negative charge here, positive charge there, that is when the capacitor is once again fully charged, but in the opposite direction. Okay, you have positive here, negative there, and all the energy once again becomes electrical, carried by the capacitor. And what happened to the inductor then? At that point, the inductor should carry minimal magnetic energy, which is 0, which means at that point the current is 0, which means you have a flat curve here because dq dt, which is a current, is 0 at this point. So you have to rise again. After that, you can rise again. You see the similarity between these two cases? Okay, so we can expect, qualitatively, we can expect this case, there will be an oscillation of charges back and forth, positive, negative, positive, negative. This is therefore an example of the ever so important electromagnetic oscillation. Okay, again, we're going to exploit the similarities between the mechanical oscillation and the electromagnetic oscillation. Now, what we did so far was only a qualitative match between these two cases, but if we want to sort of translate these results from mechanical case into electromagnetic case, we have to establish a one-to-one correspondence between quantities here and quantities there. Let's see how this can be done. Okay, now in the electromagnetic case, I can apply Kirchhoff's rule. Okay, Vc plus VL equals 0. There is no EMF. Okay, so we add these two, we get 0. Vc is Q over C, and VL is L di dt. Okay, L di dt. I, of course, is itself dq dt, so then di dt is the second derivative of Q respect to time. So we have that, right? Now, in the mechanical case of F equals ma, of course, Newton's second law, F equals negative case, don't forget that negative sign. Okay, don't forget the negative sign. That means when the block is pulled this way, the force acting on it from the spring is against its displacement, so it goes backwards. That's what negative sign means. M times the second derivative of x, which is also dv dt. Now, look at these two equations. This is the equation of motion of the mechanical system, and this is the Kirchhoff rule applied to the LC circuit. If I move this term to that side, okay, then you see they really match very well. In particular, Q replaces x, right? And second derivative of Q is, of course, second derivative of x. L replaces what? L replaces m. That's the parameter in front of the second derivative. And what about 1 over c here? 1 over c replaces what? Replaces k. That's the parameter in front of the x value or in front of the q value. Alright, so you see there exists a one-to-one correspondence between these two oscillations, the electromagnetic oscillation and the mechanical oscillation, if we replace q with x and also find some similarities, correspondence between the parameters. Let us draw a table, okay, for the similarities. In the mechanical oscillation, I have x. Right? Electromagnetic case, I have q. Both are functions of time. And of course, once you know x, you can find v, which is dx dt. That's the velocity. And here, similarly, you can find the current I, which is dq dt. Okay, so current I corresponds to v. Now, going further, the parameter k, is now replaced by what? By 1 over C, and the parameter M, the mass, is now replaced by the inductance L. Right? We can continue with this table, but for now, let's go back to here. If you consider the energy of the system, in the electromagnetic case, you have electrical energy stored on the capacitor plus the magnetic energy stored on the inductor. You add them up, it should be a constant. In other words, Q squared over 2C plus 1 of Li squared should be equal to a constant. Okay, by the way, the conservation of energy and the Kirchhoff rule, in other words, these two equations, they are totally consistent with one another. Okay, if you know one, you can derive the other. In fact, what I want you to do is this. I want you to take this equation, right? I want you to take this equation, and I want you to take a time derivative of every term. ddt, ddt, ddt. Of course, if you do so, the right hand side should be what? It would be 0, right? Because derivative of a constant is equal to 0. And this term will become Q over C. You can easily see that. And next term will become, this term will become L times di dt, or L times second derivative of Q. So, you take time derivative, you go from here to there. Similarly, in the case of mechanical oscillation, okay, the energy has two forms: elastic potential energy plus the kinetic energy of the block. You add them together is equal to a constant. In other words, 1 half k squared plus 1 half mv squared equals a constant. You see here, the potential is a parabolic potential. Okay, it's a parabolic potential. That is a signature of a simple harmonic oscillator. Right? There are two ways to signify that you have a simple harmonic oscillator. One is that you have a restoring force that's linear to the displacement. Okay, x to the first power. The other is you have a potential energy that goes like a parabola. Okay, it goes like a function of x, like an upward parabola. You have a similar situation here. You see, if you consider this term to be analogous to the 1 half mv squared, because I is analogous to v, then that term would be analogous to the potential energy, or 1 half kx squared. You see, just like here, you have a parabolic dependency. Okay, q squared, right? Positive q squared. So you can expect that you will have an electromagnetic oscillation, just like you here you have a mechanical oscillation. Okay, this analogy is very important to us, once again, because whatever result we already obtained here, we can sort of just use the correspondence and then we can translate it to the language of electromagnetism. Okay, we're going to do that in just a minute, but in order to understand the process better, what I want to do now is I want to compare these two oscillations side by side by studying the behavior of each system within one full cycle. Okay, this is from our textbook. Let's see now. Let's start with a situation in the electromagnetic case where the capacitor is fully charged, okay, and yet there is no current at this moment. So you just closing the switch. So you see there's no current in the inductor, but the capacitor is fully charged. So Q is now positive maximum. Okay, so if I have to plot Q as a function of time, I'm going to start with a maximum value. Okay, I'm going to start with a maximum value at this point. Meanwhile, since Q is analogous to X, okay, to the displacement, this situation is analogous. It corresponds to the case of a spring being extended fully to one side. I pull the mass all the way to that side with a displacement A. A corresponds to the amplitude of Q, or Q maximum. And I let go it from rest. So V is equal to 0, just like here, current is equal to 0. Okay? So, what happens next? What happens next is that time goes by. So, between here and there, there's a quarter of a period. See, I drew a whole period between here and there. So, I'm looking at the time interval between here and there, 1/4 of a period. Okay? So, 1/4 of a period later, what happens? The current gradually increases from 0. Just like here, the speed gradually increases from rest. Okay, and by the time the block passes the equilibrium position, okay, so x equal to 0, at that point, in the electromagnetic correspondence, that is when Q equal to 0, right? Because again, Q corresponds to x. So the capacitor is now fully discharged. There is no energy stored in the electrical form. All energy is now in magnetic form, which means the current has to reach a maximum. or correspondingly the speed has to reach a maximum, right? Make sense? Okay, so at this point the Q goes down to 0. Okay, Q goes down to 0. And meanwhile, what's happening to the current? What's happening to the current? The current starts from 0 at that moment, and it picks up, right? It reaches a maximum value at that point, just like the velocity reaches a maximum value here. So this is like a cosine function, right? And then the current behaves like a sine function. So the current goes up like this. It goes up to a maximum at the same moment of t over 4. Now, next, you go from here to there. Another quarter of a period later, what happens? Mechanically, we know this guy starts from the equilibrium position, keeps on pushing, right? Keeps on pushing until it fully compresses the spring. Okay, it slows down in the process, so it loses kinetic energy while picking up potential energy when the spring is compressed further and further. Similarly, in the electromagnetic case, you start with no charge, okay, or no electric energy, with a lot of current, and then gradually, as the current continues to flow, no more charges will be stored on this plate and that plate, so gradually you recover electrostatic energy on the capacitor, but you can lose magnetic energy on the inductor in return. Now, when the spring is fully compressed, the block is not moving. Correspondingly, when the two plates are fully charged, there's no current anymore because all energies are electric, no magnetic energy, so the current is 0. Okay, so let us continue to plot the second quarter of period between here and there. In terms of charge, the charge is now going to be reversed, will be negative, okay, because now you start with a positive charge on this side instead of that side, right? And meanwhile, the current should start from maximum value and gradually decrease to 0, just like the speed gradually decreases to 0. Okay, and then what happens next? What happens next? You go from here to there. That's the third quarter of the period. Okay, you start from a fully compressed position, you go backwards, right? So now you go backwards. Okay, you gradually lose potential energy of the spring and you gain kinetic energy until you go back to the equilibrium position with maximum possible speed. What's the corresponding electromagnetic case? You start with a lot of positive charge here and a lot of negative charge. So now there will be a backward flowing current, okay, which gradually increases the magnetic energy on the inductor, and then the energy is going to be gradually lost in electrical form on the capacitor. So Q will start from the negative maximum value, and gradually it will go to 0, at which point no electrical energy, only magnetic energy, which means the current is now maximum, okay, has a maximum magnitude. So the current at this moment reaches a maximum magnitude, just like the velocity reaches a maximum. Okay, see, current goes maximum, but the current, you see, now it's flowing this way instead of that way, so it's reversed. Okay, this is positive, this is negative. Okay, now finally, the last quarter of the of this period. Okay, you start from mechanically. You start from equilibrium position. You have a lot of speed, a lot of kinetic energy, but you have no potential energy. Okay, and then you gradually the block will be moving forward, which will then stretch the spring, right? So the spring will get stretched. The spring exerts a negative force on it. The block will slow down, slow down, slow down. Eventually, it's going to stop after another 1/4 of a period. Okay. Electromagnetically, what happens? Well, just like here, you start with no potential energy. Here, you start with no electrical energy. Okay. You have maximum speed. Here, you have maximum current. Now that current, of course, is going to charge up the capacitor again. So the capacitor would deposit on positive charge, negative charge. And after a quarter of a cycle, you have again established a maximum amount of positive charge here, a maximum amount of negative charge here. And this is when again all the energy becomes electrical, no magnetic energy, or no current, just like here, no velocity. Okay, so as far as the charge is concerned, you start from 0 value here, and you gradually go back to a maximum. You gradually go back to a maximum like this, right? And then as far as the current is concerned, you start from maximum value and gradually decrease to 0, just like the speed here goes from maximum value and gradually decrease to 0 when it's fully stretched. when the spring is fully straight. So we go like this. Okay, so you see the red curve is how the charge on the capacitor changes as a function of time, and the green curve is how the corresponding current changes as a function of time. And of course, I equals dq dt. So when Q is a maximum, when Q is a maximum or a minimum, that means dq dt at that moment is 0, which means current is 0. Okay, that is of course required by the conservation of energy. So this is an analysis of what happens in one whole cycle, both in a mechanical case that we are familiar with from physics 1b and the electromagnetic case, the LC circuit. So you can see clearly the correspondence between these two cases.